So far we have only grouped, we have somehow shaped the solution to a situation which contains known functions, well behaved like sine, cosine, and exponential. But we have also collected a number of unknowns, namely these ones. So we have an unknown E31, E21, and E22, those, let's say, integration constants, unknown E0, and moreover, and which is more the trouble spot, the unknown is the Kx. Why that is the trouble spot? Because those constants are quite simply multiplying functions. So in fact, they form a linear set of equations. But this is in no sense linear. It's always hidden inside a cosine, sine, or exponential. Not a very linear function at all. So now we have used the first part of knowledge. We knew that the solution must obey the law of physics, which is expressed in the wave equation. But the wave equation itself will not help us anymore. This is all we can resource out of that. Now we should have to use the boundary conditions. So, let us use a boundary condition. So let's say at the boundary where we have the x-coordinate equivalent to A, so just at the boundary between the filling of the waveguide and the enclosure, metallic or other layer on it, at the inner boundary, the x-coordinate is equivalent to A according to the picture I have made at the beginning. So we can express field components at this boundary. Namely, we will know that from the inner side, another remark, at this place we will choose only one position so that we will make a cut at some z. To make it in the simplest way, let's do it at z equivalent to 0, because the wave propagates along the structure with all its components. So making relation between them, we can forget about this e raised to minus jkzz. So we can only work with those black written parts of the formulas. And now we can write a set of equations. For example, we can write that at this boundary, the tangential field components upstairs and downstairs must be equal. It would be more proper for an equation to put it down in a manner that the electric field strengths on the upper end of the boundary minus the electric field strengths on the down side of the boundary makes 0. That means that I put down, I start with the inner side, E0 times cosine kx. Now I know the x, it's A, kxa. That's the field component Ez in the z direction, minus. Now we have the second layer. We will have this equation. So E21 sine kx a minus E22 cosine kxa is 0. So we have this equation, and to be honest with you, I have to also add some numbers. So this is the k in the first layer, this is the k in the second layer, this is the k in the second layer. But now this equation is complete. To have the same notation, I would add brackets, which is more or less clear anyway. So I have an equation, and that equation is equal to left side is here and the right side is 0. Now I can, for example, put down another equation for another end of the boundary. So upstairs, between the boundary, between this layer and the outside of the waveguide, we can also form an equation. I will not do it now, but I will show how I would do it. So I would write, for example, E21 sine kx in the second layer times, let's say that this is b, times b, the end would be b, minus E22 cosine kx in the second layer times b. And now I would put down plus E31 e raised to minus jkx in the third region times b is 0. In fact, this is something that could be interpreted as a set of linear equations. If you put those equations into right columns, you would have something like E0, E21, E22, and E3. I have written 3,1, which are the unknowns. Then there is a set of a matrix A. For example, element 1, 1 of this matrix is cosine kxa. Element 1, 2 is sine k in the second layer xa, and vice versa. So you would have a set of equations. In fact, I have an equations of the type a times a vector is equivalent to a 0 vector. I have 4 unknown constants here, and I have formed a set of equations in order to be able to handle the fifth one, the kx, which is most uneasy. Well, and now there is an important rule of mathematics or algebra, which says, or tells us, that this equation, which is a linear equation, a linear set of equations with its right side equivalent to 0 or 0 vector, has a solution if and only if the determinant of that matrix A is zeroed. If the determinant of the matrix is 0, it is the same like to tell, okay, the matrix A has 2 lines, at least 2 lines, that are linear dependent. That's the equivalent to tell, I can select one of those constants arbitrarily, and then find out the others out of the equation. But one of them, or at least one of them, can be set arbitrarily. In fact, we would possibly be happy if only one of them is set arbitrarily, because that means, in fact, that we can propagate a 1 watt, 2 watt, 1 kilowatt signal. We will just scale it by this constant. The others are somehow dependent on this one chosen. And in fact, if you consider that, this is the only way how a transmission line could work. It should propagate waves of different intensity. So we would have to find out the situation where the matrix A is singular, that therefore has a zero determinant. Okay, then we can form it in this way. This seems to be a very simple equation, but what is the matrix A dependent on? Well, we have a given geometry, like the distances A and B. We have given material properties, like permittivity, permeability, and conductivity in all of those three regions. We have, of course, something which we could vary, and that's frequency, but at a given frequency, we still do not know the value of the propagation constant along the axis Z. We can find out the case for any of the regions, and we have the formula on the screen, on the table. But now we should find out whether there is any kx or kz which satisfies the condition of the zero determinant. So let's call it that the A is dependent on kz. Then, of course, in each layer, depending on the kz, we have given the kx, which is seen in this equation, and for some values we would get a zero value for the determinant. Now this is a bit tricky because kz is not a real number. It would be a real number in a lossless waveguide. Then it would be much easier. But we have a complex number, so in fact we have to search for two variables: the phase constant, the phase part mostly called beta, and the loss factor called alpha, and we have to find the zero of that determinant, and then we can calculate anything we would like to. Now, first, in fact, we are ready. I mean, we are ready with all ideas. The rest is just hard work. Possibly hard work for Lumberman. You have to derive equations, you should not make mistakes, and finally you get anything you want. I will put within the Teams a PDF output of my MATCAD file where I have done things like Poynting vector, how much power density flows into the walls because there are losses and so on. So this file will be shared with you. There is also one point I would like to raise. If you plot the determinant as a contour plot for a given geometry and permittivities and so on, you would have the real part of the kz on this axis and the imaginary part on this axis. So this is affecting wavelength, this is affecting losses. For a waveguide that is without any losses for the initial nice case of two ideally conductive plane parallel sheets, you would have a first zero somewhere here. Where here? Well, when the distance between those two walls is 1/2 wavelength. That's the beginning of propagation of the dominant mode. 2 times more farther would be a second zero, which would mean that you have the organization of the fields already in 2/2 wavelengths between those two walls, and vice versa, it's infinite. But there will be no other zeros of the determinant. Once you start to include losses, you would be surprised to other zeros somewhere in the plane. First of them would be strictly close to the imaginary axis. So those would be modes which barely propagate. They are close, not exactly on the axis, so they have some positive real part. But they barely propagate, but they are quite a lot damped. While with an ideal waveguide, they would be out. With a lossy waveguide, you have a number of propagating modes anytime. Just some of them propagate very, very poorly. But you will find more points, and as the determinant is not behaving very well, it is not an easy task to find out all of the complex solutions of the general equation determinant A depending on kz is 0. But anyway, it's possible. So that's the second remark. Now please, I would like to ask you 4 questions. And please make sure that you understand why I have tried to zero the determinant. This is a trick that is used quite often. So it's an important trick in waveguide or transmission line solution. And now I'm listening for your questions. So I can't see anything in chat. I can't see hear a question. And therefore I would make a few more comments. You know, I will reveal things that are obvious, but only after you experience a problem with them. So the first thing you should bear in mind, the whole procedure we have so far used seems to work fine as far as you try to solve the original thing, which was a waveguide with very low or even no loss dielectrics and then a very good conductive wall. Now, in fact, this is very nice, but then you might have one problem, and that is with the condition just out of the waveguide. We have chosen this solution, and based on the fact that Kx in the outer region is positive, I mean that the real part of the Kx is positive, the wave damps with distance from the waveguide, which we need to cover the important property of limited energy. So we need a real part of Kx in the third region bigger than 0. Now there is some material. Let's think that we have K3, that's not K raised to the third order, so I will circle it. We have the number K3. Let's, for example, well, okay, let's make it lossless. So the K3 is omega times mu epsilon, or square root of mu epsilon product, which is taken all in the third media. Now let us have inside the waveguide, somewhere in the system there are some losses. So Kz would be would have a real part, let's call it beta, minus J alpha. This is the damping. If the structure is lossy, this must be, the alpha must be a positive real number. So now we have the equation to find out Kz in the third region, or Kx. So Kx3, we had it on this paper some hour ago. Kz in the third region is equivalent to Kz in the first region, is a common Kz. So if this is lossy, it brings those losses into the equation for Kx in the third region. Kx is a square root of K in the third region squared minus K Z in the third region, or Kz, because that's common for all regions. And now look, if this is a complex number, you would get a complex number here, and you are